In the last two lectures, we talked about this particular Diophantine equation, a square plus b square equal to 3c squared. And we also know that a modular check will tell us that the right hand side, the 3c square portion, this gives us 0 or 3 when divided by 4. So that's the remainder that we get when divided by 4. And we also know from the previous lecture that any square number, that is, any square number means if you take any integer and square it, then it spits out remainders 0 or 1 modulo 4. Now, let's look at the left hand side now. We know the right hand side gives remainder 0 or 3. What about the left hand side? So, a square plus b square, what are the possibilities? The possibilities are that both of them provide remainder 0, or one of them gives 0 and one of them gives 1. This can happen in two ways, or both of them provides 1 as remainder. So if both of them give 0 as remainder, then we get 0 as remainder as their sum. If both of them gives 1 as one of them gives 1 as remainder, then we get 1 as their sum. And if both of them gives 1 as remainder, then 2 is the sum of the remainders. So we have these four possibilities. So the left hand side, a square plus b square of this equation, can give these four values, these four 0, 0, 1, 1 and 2 as remainders. Alright, so the good news is that these three things cannot happen, right? Because remember that the right hand side is 0 or 3. So these are neither 0 nor 3. These are 1, 1 and 2. So these two cases cannot happen. The only case that can happen is the first one. So let's highlight that. This is the only case that can happen. So a square gives 0 as remainder modulo 4. B square gives 0 as remainder modulo 4. And c square gives 0 as remainder modulo 4. So that's the only situation where both sides of this equation matches up modulo 4. Now, we are almost done with this problem. When a square, b square and c square are all 0 modulo 4, this necessarily means that all of these are divisible by 4, right? That's how it can give 0 as remainder modulo 4. So that can only happen if a, b, c are all even numbers. That can only happen if a, b, c are all even numbers. But you can quickly realize that that case can also be taken care of. Why? Because if a, b, c are all even numbers, we can divide each of them by 2's or some power of 2. We can divide each of them by 2 or some power of 2. And eventually, if we divide a, b and c by large enough powers of 2, then one of them will be odd. So let's quickly put that argument in place. So this is often called infinite. This is a form of infinite descent. So if a square plus b square equal to 3c square, if we want to find integer solutions of this particular equation, we can assume that not all are even. Why? Because if all are even, then we can just delete all to as many 2's as possible, divide by dividing both sides by as many 2's as possible. We can delete as many 2's as possible, and we will probably, after division, we get an equation like this. And in this particular equation, this is after dividing both sides by a large enough power of 2, we have three integers a1, b1, c1. Not all of them are even now, and that satisfies this equation. But we know that that is not possible. Why? Because whenever three integers satisfies that equation, they all are necessarily even by our investigation of modulo checks. So, in other words, there are no integer solutions to this equation. Thank you for watching, and keep subscribed to our channel if you want to find more videos like this. Thank you.